Hello everyone, in this video we are going to discuss about the periodic trends in physical properties of elements. We will be discussing about the ionization enthalpy in this video. See, we have already discussed about the atomic radius and ionic radius in our previous videos, which will be available in the playlist. See, some elements have tendency to lose electrons. The quantitative measure of the tendency of an element to lose electrons is actually given by its ionization enthalpy. It is represented by delta IH, ionization enthalpy. See, it is actually the energy required to remove an electron from an isolated gaseous atom in its ground state. That is, when a gaseous atom is in its ground state, then to remove an electron from it, how much energy is required? That is actually called as ionization enthalpy. You see, the first ionization enthalpy for an element X, it is the enthalpy change for the reaction depicted in this equation. That is, we have an element X here. Okay, this equation shows that X is an element which is in the gaseous state. That is why X within brackets G. Okay, so this is an element in its gaseous state. This element loses one electron to form a cation, that is a positive ion X plus. Okay, so first ionization enthalpy means it is the energy required to remove the first electron, which is the most loosely bound electron, from a gaseous atom in its ground state. So in this equation, X is any element or atom. This equation shows that the element X is in its gaseous state. This element loses one electron to form a cation or a positive ion. The energy required or releasing energy for this process, that is actually the first ionization enthalpy. See, the unit of ionization enthalpy is kilojoule per mole or kilojoule mole raised to minus 1. Now, second ionization enthalpy, that is the energy required to remove the second most loosely bound electron. That is, it is the energy required to carry out this reaction X plus, which is in gaseous state, and by losing one electron we are getting X2 plus. That is, after the first electron has been removed, X became X plus. Now, when we remove the second electron, this X plus becomes X2 plus. And the energy required to carry out this reaction, that is called as second ionization enthalpy. See, second ionization enthalpy IE2, ionization enthalpy 2 means second ionization enthalpy, IE1 which is the first ionization enthalpy. Second ionization enthalpy, it is always greater than the first ionization enthalpy. It is because of the increased nuclear charge and decreased electron shielding. That is, second ionization enthalpy is the energy required to remove an electron from the X plus ion. So, when we consider X plus ion, more number of positive charges are there and less electrons are there. It is more difficult to remove an electron from a positively charged ion than a neutral atom. In the same way, third ionization enthalpy will be higher than the second ionization enthalpy. See, when the term ionization enthalpy is used without any qualification like second ionization enthalpy, first ionization enthalpy, etc., then it refers to the first ionization enthalpy. So you see, second ionization enthalpy, it is always higher than the first ionization enthalpy. Okay, because second ionization enthalpy is the energy required to remove an electron from the X plus ion, in which we have more number of positive charges than the negative charges. So it is more difficult to remove an electron from a positively charged ion than a neutral atom. Similarly, the third ionization enthalpy is greater than the second ionization enthalpy. Here you see this figure. The first ionization enthalpies of elements having atomic numbers up to 60 are plotted in this figure. Along the y-axis, we have the ionization enthalpy in kilojoule mole raised to minus 1, Along the x-axis we have the atomic number Z. Okay, now you see the periodicity in this graph. See the periodicity in this graph. You can see that the first ionization enthalpy increases from hydrogen to helium across the first period. Then from helium to lithium decreases, that is down a group top to bottom. From lithium to neon, the first ionization enthalpy increases. Then from neon to sodium, you see it has decreased. Again from sodium to argon, the next period, the ionization enthalpy increases. The same nature is repeated. Here, you can find the maxima at the noble gases. See the maxima here for helium, neon, argon, krypton, xenon. So you see, we can find the maxima at the noble gases. See, noble gases have closed electron shells and very stable electron configurations. See, lithium, sodium, potassium, rubidium, cesium, they are alkali metals. And minima occur at the alkali metals. That is, alkali metals have low ionization enthalpies. See, noble gases have high ionization enthalpy and alkali metals have low ionization enthalpy. See, the low ionization enthalpies of alkali metals are directly connected to their high reactivity. Because alkali metals have low ionization enthalpy, making it easy to lose one electron to form a positive ion or a cation. Easily losing one electron makes alkali metals highly reactive, eager to participate in chemical reactions. Now, you consider this figure. It actually shows the first ionization enthalpy. First ionization enthalpy is given measured in kilojoule mole raised to -1. Along the x-axis we have the atomic number. So this figure actually shows the first ionization enthalpy of elements of the second period elements actually as a function of atomic number. Second period elements means lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay. So it is very clear from this figure that across the period you see the first ionization enthalpy increases. Okay. Now you consider this figure. This actually shows the first ionization enthalpy of elements of the first group, that is alkali metals, as a function of atomic number. See, lithium, sodium, potassium, rubidium, cesium, first group alkali metals. It is very clear from this figure that the first ionization enthalpy decreases. Okay, first ionization enthalpy decreases as we descend the group. See, ionization enthalpy and atomic radius are closely related properties. See, atomic radius increases down a group, that is from top to bottom, and ionization enthalpy decreases down a group. That is, when we consider elements in a group, as we move down, more energy levels are added and electrons are farther from the nucleus. And atomic radius increases. This makes it easier to remove an electron from an atom that is lower ionization enthalpy. And across a period, atomic radius increases. Right, across a period, atomic radius increases. Across a period, atomic radius decreases and ionization enthalpy increases. Okay, down a group from top to bottom, atomic radius increases, that is ionization enthalpy decreases. Across a period, atomic radius decreases and ionization enthalpy increases. That is, across a period, electrons are closer to the nucleus of the elements and making it harder to remove an electron, that is higher ionization enthalpy. That is, ionization enthalpy and atomic radius, they are inversely related. Smaller the atomic radius, higher the ionization enthalpy. Larger the atomic radius, lower the ionization enthalpy. So you see, down a group, atomic radius increases, so ionization enthalpy decreases because they are inversely proportional. Across a period, atomic radius decreases, that means ionization enthalpy increases because they are inversely related, proportional to each other. So to understand these trends, we have to consider two factors. One is the attraction of electrons towards the nucleus and the repulsion of electrons from each other. See, the effective nuclear charge experienced by the valence electron in an atom will be less than the actual charge on the nucleus because of the shielding or screening of the valence electron from the nucleus by the intervening core electrons. See, we have already discussed about the screening or shielding effect in our previous video, in which we have discussed the screening effect or shielding effect in detail. So here you see, let us consider one example of this element, lithium. Its atomic number is 3, electronic configuration 1s2, 2s1. So here we have, you see, for lithium there are 3 positive charges in the nucleus. 2 electrons are in the first n equal to 1 principal quantum level, and there is 1 electron for n equal to 2 principal quantum level. So here the valence electron is the 2s electron. It is shielded from the nucleus by the inner core of 1s electrons. Okay, see, inner core of 1s electrons, that means 2 electrons are there in the innermost energy level, that is in the 1s level. Okay, 2 electrons are in the 1s orbital. Due to this, the valence electron experiences a net positive charge which is less than the actual charge of plus 3. Okay, in general, shielding is effective when the orbitals in the inner shells are completely filled. For example, in alkali metals, they have only 1 electron in the outermost orbital, and all other innermost orbitals are completely, or all other inner orbitals are completely filled. See, we have already seen this case in lithium. Now, if you consider another alkali metal, which is sodium, its atomic number is 11. So, electronic configuration 1s2, 2s2, 2p6, 3s1. Okay. Here also, only 1 electron in the outermost orbital. Okay, here the valence electron is the 3s electron. It is shielded from the nucleus by the inner core of 1s and 2s 2p electrons. So here you see, for sodium 11 protons are there in the nucleus, so 11 positive charges are there in the nucleus. Okay, and 8 electrons are here in the see, we have 1s2. So in the first shell, K shell, we have 2 electrons. Okay, then in the second, this is n equal to 1. For n equal to 2 quantum level, we have 8 electrons. Okay, then for n equal to 3 principal quantum level, we have only 1 electron. Okay, that is, here this valence electron, which is the 3s electron, will experience a net positive charge which is less than the actual charge of plus 11 because of the shielding effect of these inner core electrons. Now, let us consider the second period elements from lithium to fluorine. See, when we move from lithium to fluorine across the second period, successive electrons are actually added to orbitals in the same principal quantum level. See, here the electronic configurations of each element from lithium to fluorine are given. See, in every one of it we have 1s2, 1s2, 1s2. Okay. Then you see here 2s, 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 then 2p, 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 like that. So here you see across the second period, the successive electrons are added to the orbitals with the same principal quantum number, because here you see in beryllium we have one more electron than lithium, so that is added to 2s orbital. So n equal to 2. Same, you know the principal quantum number, n is equal to 2. Then for boron we have one more additional electron, so that goes to 2p. So anyway n is equal to 2. Okay, here also n is equal to 2. Then here when we consider carbon, we have one more electron than boron, that goes to the 2p level. So here also n is equal to 2. Okay, that is when we move from lithium to fluorine across the second period, the successive electrons are added to orbitals in the same, same principal quantum level. Here, electrons are added to 2s and 2p orbitals, that is same principal quantum level, n is equal to 2. And across the period, the shielding of the nuclear charge by the inner core of electrons does not increase very much to compensate for the increased attraction of the electron to the nucleus. That is, across the period, the inner core, that is 1s2 here, that is closest to the nucleus, which is 1s2. So across the period, the inner core remains unchanged. And next level also has almost constant electrons, that is 2s2. Except for lithium, here we have 2s1, but all other elements are having, the same constant electrons in 2s. Okay, 2s2, 2s2, 2s2. Okay, so shielding effect provided by the inner electrons are almost constant. Since the atomic number increases from lithium to fluorine, effective nuclear charge increases and this dominates the shielding effects. See, shielding effect means inner core electrons reduces the nuclear charge. Effective nuclear charge means it is the net nuclear charge experienced by outer electrons. So when we move from lithium to fluorine across the period, atomic number increases. Okay, and effective nuclear charge increases. Here we have 3 plus charge, here we have 4 plus charge, here we have 5 plus, 6 plus, 7 plus. Effective nuclear charge increases. And effective nuclear charge means that is a net nuclear charge experienced by the outer electrons. Definitely outer electrons won't be experiencing the same plus charge here or 6 plus charge here. But anyway, the effective nuclear charge increases and that dominates the shielding effect. That is, across the period, increasing nuclear charge outweighs or dominates the shielding. Consequently, the outermost electrons are held more and more tightly and the ionization enthalpy increases across a period. See, ionization enthalpy is the minimum energy required to remove an electron from a neutral atom or molecule in its ground state. So, across a period, ionization enthalpy increases. Ionization enthalpy increases means more energy would be required to remove an electron from a neutral atom in its ground state. And you see, as we go down a group, the atomic radius increases, the outermost electrons move farther from the nucleus. So, inner electrons provide increased shielding and shielding effect outweighs or dominates over increasing nuclear charge. So, down a period, shielding effect outweighs or dominates the increasing nuclear charge. So, ionization enthalpy decreases down a group, that is from top to bottom of a periodic table. Ionization enthalpy decreases means the removal of outermost electron requires less energy down a group. So, across a period, increasing nuclear charge dominates the shielding effect and ionization enthalpy increases. Down a period from top to bottom of a periodic table, shielding effect dominates over increasing nuclear charge and ionization enthalpy decreases. But here you see, in this figure which we have already discussed, we can see that the first ionization enthalpy of boron, which has an atomic number 5, it is 801 kilojoule per mole or kilojoule mole raised to minus 1. And ionization enthalpy of beryllium, which has an atomic number 4, which is less than boron, it is actually 899 kilojoule mole raised to minus 1. That is, the first ionization enthalpy of boron with atomic number 5 is slightly less than that of beryllium of atomic number 4, even though boron has greater nuclear charge. That is, first ionization enthalpy of boron, it is 801 kilojoule per mole. It is slightly less than that of beryllium. Beryllium has a first ionization enthalpy 899 kilojoule per mole. You see, beryllium, it has atomic number 4, electronic configuration 1s2 2s2. For boron, atomic number 5, so electronic configuration 1s2 2s2 2p1. So when we consider the same principal quantum level n is equal to 2, the s electron is attracted to the nucleus more than a p electron. That is, when we consider the same principal quantum level, here you see the last one is n is equal to 2. That is, valence electrons are in the principal quantum level n is equal to 2 for both beryllium and boron. So when we consider the same principal quantum level n is equal to 2, the electrons in the s orbital will be attracted more to the nucleus than the electrons in the p orbital. See, in beryllium, electron is removed during ionization is an s electron, whereas the electron removed during ionization of boron, that is a p electron. See, the penetration of a 2s electron is to the nucleus, it is more than that of a 2p electron, because s orbitals have spherical symmetry which allows closer approach to the nucleus, and 2s electrons will experience stronger nuclear attraction and they are tightly bound and have higher ionization energy for 2s electrons. So more energy is required to remove an electron from the 2s orbital than from the 2p orbital. See, p orbitals are dumbbell shaped orbitals which keep electrons farther from the nucleus. Hence, a 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electron in beryllium. Therefore, it is easier to remove the 2p electron from boron compared to the removal of a 2s electron from beryllium. So you see, it is easy to remove a 2p electron from boron than beryllium means boron has smaller ionization enthalpy than beryllium. That is, less amount of energy is required to remove an electron from boron than when it is compared with a beryllium. Okay. Similarly, the first ionization enthalpy of oxygen, which has atomic number 8, it is less than or smaller compared to the nitrogen. That is, you consider this figure again. Here we have the first ionization enthalpies of second period elements. Here you see nitrogen has an atomic number 7 which has an ionization enthalpy 1402 kilojoule per mole. Oxygen has an atomic number 8 which is greater than nitrogen, but its ionization enthalpy is less than nitrogen, which is 1314 kilojoule per mole. That is, the first ionization enthalpy of oxygen, it is smaller compared to nitrogen, though oxygen has greater nuclear charge, because in oxygen we have 8 positive charges in the nucleus, in nitrogen we have only 7 positive charges in the nucleus. That is, the first ionization enthalpy of oxygen, it is less than that of the first ionization enthalpy of nitrogen. Because you see, when you consider nitrogen, its atomic number is 7, electronic configuration 1s2, 2s2, 2p3. So valence electrons are in 2p level. When you consider oxygen, its atomic number is 8, electronic configuration 1s2, 2s2, 2p4. So valence electrons are again in the 2p level. Here you see, the 2p electrons in the nitrogen atom reside in the different atomic orbitals px, py and pz according to Hund's rule. That is, when we consider this p orbital, we know that it is actually divided into 3 p orbitals. One is px, py, pz. This is 2p orbital now. So one is 2px, 2py and 2pz we have. And according to Hund's rule, the 3 electrons in the 2p orbital now, it will be filled in such a way that first one electron goes to each 2p orbital Okay, so here we have three 2p electrons. So one electron will occupy the 2px orbital, one electron will occupy the 2py orbital, and one electron will occupy the 2bz orbital. But in oxygen atom we have four 2p electrons. So according to Hund's rule, one electron will first occupy the 2px orbital, one electron in 2py and one electron in 2pz. Now the fourth electron will come to the 2px orbital and will get filled here. That is, according to Hund's rule, the two of the four 2p electrons will occupy the same 2p orbital, and that results in an increased electron-electron repulsion, because you see two electrons are here in the 2px orbital. When two electrons are near to each other, electrons are having same charges, negative, negative, there will be a repelling force, there will be a force of repulsion between them. So there will be an increased electron-electron repulsion here in the case of oxygen. So it is easier to remove the fourth 2p electron from oxygen than to remove the 2p electron from the nitrogen. That is why the first ionization enthalpy of oxygen, which is less than the first ionization enthalpy of nitrogen. So in this video, we have discussed about the ionization enthalpy. We have already discussed about the ionic radius, atomic radius, and we will be discussing the electronegativity, electron gain enthalpy, etc. in our videos, which will be available in the playlist. I hope this is clear to you. Thank you.